Hello and welcome to a short presentation on how the National Weather Service issues a tornado warning. This presentation serves as a peek into the decision and warning process with a demonstration using a live simulation from April 27th, 2011. First, all National Weather Service radar warning operators will analyze the atmospheric environment before and during the severe weather event. The larger questions of what is the favored storm mode and direction of the storms going to be needs to be answered. There is a big difference in warning strategy and management if dealing with, say, a squall line versus a supercell. How will storms change in time? Are they going to remain separate or grow into a line? This is important to know. Lastly, what will the storm be capable of? Is this a day for one or two brief tornadoes, or are strong tornadoes possible? What about violent long-track tornadoes? Answers to these questions will help the warning operator to envision the overall storm evolution and overall warning management. Now, when storms develop, the radar warning operator will analyze the storm structure into 4 dimensions: horizontal, length and width, vertical, altitude, and in time, to see trends of strengthening or weakening motion and overall storm structure. They will do this looking at reflectivity, or the rain and hail distribution in the storm. They will look for the appearance of a hook, notch, or small appendage. A large overhang of reflectivity in the vertical indicates a strong updraft is present. The presence of a bounded weak echo region indicates a strong rotating updraft. In conjunction with reflectivity, they will also look at storm relative motion, or SRM, which is the magnitude and direction of winds within a storm. When outbound and inbound winds are in close proximity or touching, rotation is tightening, and the likelihood for a tornado is generally increasing. Whenever green and red are such, it is known as gate-to-gate shear, or gate-to-gate velocity, or also known as a couplet. Also, vertical continuity of a couplet helps provide additional confidence to an operational warning forecaster, but is not always present in some cases. So, taking a quick look at some reflectivity examples, we can note a small notch there located near Nidayuma. In this next example, we're looking at the same storm, but we're looking at it at several different levels. Up here in the top left, we are looking in the lowest level. And as we go to the right, bottom right, and then back to the bottom left, we are going up in altitude, or in the vertical. We can note a small notch located here just to the southwest of Norman Park. And going up in the vertical, we notice that the stronger reflectivity values, or higher reflectivity values of yellow, oranges, and reds are overhanging this area of lower values. So this is indicative of a strong updraft. Now, taking a look at this similar storm, but as a cross-section in the vertical, we can definitely see the overhang much more clearly. Very weak reflectivity is noted down here below 10,000 feet. And a really strong overhang is located and noted here between 10 and 20,000 feet. In another example from a cross-section, we have another strong overhang located right here above weaker reflectivities right here. In addition, this is also a bounded weak echo region, so these areas of lower reflectivity right here are being centrifuged out to the right and then to the left as a strong rotating updraft is present. Now, taking a quick look at storm relative motion, we have the corresponding reflectivity and storm relative motion, or velocity. Over here on the right, we have a supercell with a strong hook or appendage, and we have outbound winds indicated here by red, and inbound winds indicated here by green. On this next example, another strong hook / appendage, and in addition, we are noticing a strong outbound and inbound. At this point in the life cycle of this supercell, it would certainly have a tornado warning on it already. Here's another example from a squall line moving through portions of northeast Mississippi near Macon. There is a somewhat appearance of a hook or notch right here, as well as the storm relative motion being indicative of outbound winds in the red and inbound winds in the green, where couplets are developing along the leading edge of this line. Sometimes reflectivity can be a bit messy and may not be as beneficial for trying to look for appendages, notches, or hooks. But taking a look at the storm relative motion just to the west of Pelahatchie, we have some outbound winds and inbound winds forming a small couplet. One last example, we are now looking at velocity or storm relative motion in the vertical. So just as that past example of reflectivity, we are looking at the lowest levels over here in the top left, and then going upwards in altitude in the top right, down to the bottom right, and to the bottom left. So in the lowest levels we have outbound winds right here, inbound winds right here, and going up in the vertical we can see that that couplet continues. So once we reach that trigger point, once the decision to put a tornado warning on a storm is made, the full process from decision to drawing the warning shape to formatting the warning text is completed quickly and accurately. Generally, this whole process takes 1 minute or less. The warning must take many things into consideration: the past, present, and possible future storm motions, the area that needs to be warned, which areas of the counties, which cities, how fast is the storm moving, how to draw the warning polygon or the warning shape itself. Is a Doppler radar indicated, or have reports of damage or tornadoes occurred with the storm that was already previously warned upstream? What can be added to the text to emphasize the magnitude of the situation? Is this a tornado emergency? So once the warning has been issued, what happens? Storm analysis continues, no doubt. Storm structure in the 4 dimensions continues with reflectivity and storm relative motion, but now we also start to look at some dual polarization radar products. Lower values of the correlation coefficient product, or CC, indicate areas of where debris may be lofted. So lower values of CC in conjunction with a strong couplet supporting reflectivity indicates debris being lofted. In addition, another dual pole product, known as differential reflectivity, or ZDR, helps indicate with values of ZDR near 0 or a local minimum for more random or irregular tumbling of objects. So if these values are co-located with a strong couplet, supporting reflectivity where a possible debris ball may be located, and low correlation coefficient, a tornadic debris signature is present. So here's a quick example just of looking at reflectivity and storm relative motion. We see a very strong hook echo located right here, and within the white circle, corresponding to that white circle, we have very strong outbound winds here in red, very strong inbound winds right here in green. They have a strong 100 knot gate-to-gate couplet, or 100 knot gate-to-gate shear. Now taking another look at this same reflectivity within that same area and that same storm relative motion in the same area, we look at correlation coefficient here in the bottom right and the differential reflectivity, or ZDR, here in the bottom left. So looking within that white circle across all different panels, we have strong rotation being indicated, we have low correlation coefficients indicating that irregular shapes and objects are being picked up within the volume scan of the radar, meaning that possibility of trees, of leaves, of small debris, of 2x4s, or siding, or shingles, or portions of roofs are being lifted. Essentially, debris is being picked up by the radar. And this is continuing to be confirmed through the ZDR values as well. So when a warning radar operator sees this tornadic debris signature, the initial tornado warning text will be upgraded and updated with much stronger wording now that the radar is sampling a confirmed tornado lofting debris. So warnings are updated every 10 minutes, but may be more frequent when vital information becomes known. This can be substantial damage reports or reports from law enforcement or from emergency managers, or as a tornadic debris signature has appeared through the dual pole products. So new information that generally is included on these updates is storm location. Hazards, just as I was mentioning, is it strengthening? Have reports of damage been received? What degree of damage has occurred? For example, law enforcement reports substantial damage to homes north of Philadelphia, and we will include that in the warning text. How about the warning area? Has the storm moved out of an area that is no longer in danger? Is it about to move into an area where danger is increasing? Is a new warning needed downstream of the existing warning? So let's take a quick look at a video example of how the National Weather Service puts out a tornado warning in the April 27th, 2011 case. So just to kind of set this video up, this is the afternoon of April 27th across East Mississippi, and a tornado warning is already in effect for Neshoba County that you can see there. There is strong rotation, as evident by the storm relative motion image, just north of Philadelphia. We need to warn downstream to let people know in Winston, Kemper, and especially Noxubee counties that this strong supercell tornado supercell is on its way. So at this point, we are using a template called WarnGen that is allowing us to track the motion and speed of the storm. I have now drawn a polygon that goes downstream of the storm itself. I am making sure that this storm at this point will exit my polygon and exit the area within the valid time that the warning is located. I have drawn my polygon to make sure that if there is any deviant motion to the right, as sometimes supercells do, that I have proper amount of area. Now I am going through to make sure that this is a confirmed tornado, particularly dangerous situation per the report that we just received from the emergency manager, where extreme structure damage has been reported across portions of North Philadelphia and northeast Neshoba County. So within that text that you see being edited there, this is a confirmed large, violent, and extremely dangerous tornado located near Burnside, moving northeast at 50 miles per hour. This is a particularly dangerous situation. So once the editing of the text product has been completed, it is sent out, and this goes out to the rest of the world, including broadcast meteorologists, National Weather Service, NOAA Weather Radio, as well as many outlets also. So with that warning now being issued, we're going to go back to the previous warning and do an update to include the enhanced and upgraded wording of the strong confirmed violent tornado that is ongoing. So we are changing the area because locations in Philadelphia and further areas back to the south and west are no longer under the risk of the tornado. So we only want to warn the areas that need to take shelter, and we do not want to warn areas that do not need to take shelter. So extreme structure damage was reported north of Philadelphia and across portions of northeast Neshoba County. So quickly, this process takes place, and especially if you have multiple supercells across an area, then good communication needs to take place amongst the warning forecasters and warning operators across from each other in the office. So once that severe weather statement has been sent, here in the past 2 minutes, you have seen that a tornado warning has been issued properly, quickly, and accurately, as well as an upgraded warning has occurred and been updated as well. So, do you think you are up to the task? That is a good question. There's an online warning simulator. Find out if you have what it takes to properly decide, draw, and manage severe thunderstorm and tornado warnings from a real event. You can go to the web address below and sit in the hot seat, or you can also Google warning simulator, and that will also take you to the proper location. Thank you for viewing this presentation.